he is in diverse projects, including his own innovations such as indoor solar cooking, air flush, and industrial solar concentrator, and collaboration with the esteemed client like Oxford University in UK and Sun Beckett in the USA. He is having initiated more than 20 patents and it is commercialized numerous green technologies. He also served as a director for the International Solar Energy Society in the Freiburg, Germany for 2 years and acting as a global advisor for the Solar Cooker International in the USA since 2014. He has also worked as a consultant to the United Nations HQ, New York, and also to Ministry of New and Renewable Energy Government of India for 1 year each. His outstanding contribution have earned him the global prize at the Wintex 2018 in Indonesia, Incon First award in the individual category for 4th year from the government of Maharashtra, winner of National Grand Challenge for the design of solar cooker by Department of Science and Technology, Government of India, COEP Abhiman, and many others awards. He recognized by the institution like the Institution of India Engineers, Solar Cooker Internationals. Dr. Chandak has presented paper and the projects at over 40 conference in Germany, USA, Spain, Oman, Nepal, Portugal, the Netherlands, and India, showing his expertise in the innovation and mentoring the entrepreneur in the renewable energy and sustainability. He is a TEDx speaker. He founded the Chandak Innovation LLP. Dr. Chandak leads the company mandate to develop the proprietary innovations, offers R&D service, and mentor the aspiring the innovators and entrepreneur in the sustainability domain. He provides the service for the students and aspiring the entrepreneurs to handle the journey from the innovation to the commercialize of the product and the technologies. So I welcome such a great personality in the field of the renewable energy and entrepreneurship. So I welcome to Dr. Chandak sir. Sir, you are having the time up to the 7:30. Now the session is yours. And I request to participants, please interact with the Dr. Chandak. We are having the great time to interact with such a personality. So I welcome again Dr. Chandak sir. Please, sir.
Hello, everyone. Good evening.
Good evening.
Yeah, this is after having a look at the topic and the other speakers, even though my topic is solar energy, sustainability, and climate change. I'll talk more on solar energy, but I'll try to encompass more on the different energy and development aspects, especially for the type of audience that I have today, the research scholars and professors. I have been on both sides, like in the academics for 31 years, but just a minute. अनुराग, मेरे को 7:30 तक एक सेशन है, मैं अवेलेबल नहीं हूँ. अरे मैं 7:30 तक एक सेशन है, मैं नहीं हूँ अवेलेबल अभी. Hello. Sorry. So I have been on both sides as a professor in engineering institutes and also on the innovation development and consulting in different sustainability domain, rising to the highest level of consultation to United Nations headquarters and to International Solar Energy Society, working as a director there. A lot of these activities were simultaneous when I was also working as a professor. And then it speeded up after I left my academic career. I formed another company, and then we do more on R&D and commercialization of technologies, and also help other innovators and entrepreneurs to commercialize their ideas and technologies. So I just change tone of my lecture a bit because I have been on both sides. I just want the research scholars and the other professors to benefit from my experiences. So my lecture is not more of a theory, but more of my personal experiences. Uh, People talk about this sustainability aspect a lot. So not only solar energy, but in general, we talk about the sustainability. And from an energy perspective, the first thing that I feel is practicing it. Nothing else is better than practicing yourself. And once you start practicing it, you start enjoying the fruits of the sustainable living. It's easy for you to share with other people. It's easy for us to even teach in the classes, and it's easy for us to do research which is useful to someone, either to the industry or to the society, in whatever way you see. I have been doing a lot of these things on my own. So we are practicing solar cooking since 1999. Now 2000, so it's 25 years. Maybe I need to celebrate it now. So it's 25 years of solar cooking that we have been doing. The cooker on the right is the one which has been used since 1999. You can see the condition is not very good, but it's still working. We changed the reflector once. And the one on the left, the squarish dish, that was put into use in 2008. So it's still being in use. Maybe you can have a bit of a glimpse. These days, we are having a lot of brinjal. So this is for Bengan Bharta, roasting brinjal. And this is a video sent by one of my friends who took the cooker to US, but after assembling, he sent this video where you can hear whistling sound of a pressure cooker. So we do a lot of dishes on solar cookers, right from boiling milk to complicated dishes like thalipit, the stuffed capsicum, and omelets, and a lot of stuff like that. The other gadget that I added in 2006, I think, is a biogas plant, a kitchen waste-based biogas plant. So most of our kitchen waste, primarily the organic waste, goes into the biogas plant, and we generate biogas. Because we are not specifically putting any fuel, only digesting our own organic waste, the production is not much. But still, if I tell you about a breakup, around 40 to 50% of our cooking need are done by the solar cookers, around 15% by the biogas that we get from the waste that we generate ourselves. Recently, we are in the last stages of experimenting indoor solar cookers with heat storage. So that's a new device, but still it is in a last stage of trials. But okay, we are using it and we are generating some amount of energy that is used for cooking. This comes with a thermal storage with a battery. This year we got one patent for the composite materials that we are using for the seed storage. Then we have electric induction stoves and one microwave also. These are the devices. These are conventional electrical devices, not anything to do with solar and all. But again, the power for these devices come from a 5 kilowatt rooftop solar system that we installed 5 years back. So normally we are having a lot of energy supply of our own, like LPG we need one cylinder in 3 months, 3.5 months, and we are a big family of 7 people uh, using that kitchen. So we both, and then my son and his wife, my grandson, my daughter, my mother. So it's a big cooking stuff. In a normal run, if we don't use other devices, um, our system and the LPG cylinder will not even last for 1 month. It will be less than 1 month. In general, as a thumb rule in India, for a family of four, one LPG cylinder for 1 month is a normal standard. But here we need, for a family of seven, one cylinder in 3 to 4 months. That's because of all these different devices that we use. So the LPG is the last option after we exhaust our other options. Again, for the electricity, we have this resource. Normally, our experience is in winter, our generation is in excess, so our bill is normally negative. But in summers, we have to pay bills because we are in Dhule, a very hot place. So we have around 2 3 air conditioners operating for some time, or coolers operating. And then the generation is not enough to have that. So we may be extending our system to 10 kilowatt this year. We have solar water heaters. Again, one was installed in 1999 and the other is in 2012. As a family grew, we that one wasn't adequate, so we have now two. Uh, I must tell you, the old solar cookers were really constructed very rigid, because I can say this is still in use after 25 years, and I really appreciate the quality of solar flat plate panels which were delivered in those days. Recently, I have panels from the same company, but not as rigid. May not last for 20 to 25 years, but still okay. Even if it lasts for 15 years, people should be happy. And in most cases now, nobody uses flat plate panels. Most of the people have already shifted to vacuum tubes. And then a dryer is not a really part of our regular lifestyle, but I use for experimenting myself. So I have just one big dryer, but I just keep on doing my own experiments on it. And then energy efficiency at domestic level is a routine. Like we use all LED lamps in major areas, because the old lamps, tube lights, and old CFLs, we shifted to minor areas like toilets and storerooms. Uh, then we have star-rated appliances. Again, BLDC fans, which save 50% energy. Then we have a rainwater harvesting at home, and we have a garden waste composters. So we try to be as energy efficient and as sustainable as possible. Now coming back to understanding our R&D in engineering institute, that's a topic I have chosen. I'll stick to the energy domain because that's my area. But here I'll try to share my experiences, what has been done and how it was done. And then uh, what needs to be done now. See, all of us now understand that engineering institutes are under pressure because the placements are going down. So if there are no placements or placements are reducing, you can see that problem with the institutes. And all of us need to really think seriously about engineering education. Instead of it being the placement centric, it has to be more of a entrepreneurship centric. And the development and the converting your ideas or innovations or your research into developing that research into something which is uh, sustainable enterprise, where financially viable enterprise is what is now needed. So let it be students, let it be research scholars, let it be the professors in the institute. They should do. They should follow these enterprising practices or enterprising aptitude to convert this into to convert their regular activity of projects, the research that they do, into some kind of enterprise. Uh, Maybe I'll just take a small, share a small example. These days, I'm working as a uh, R&D person. It's more like a contract, but for Oxford University in UK. So all of us understand know Oxford University very well. So when I went to the Oxford University in 2019 to understand the assignment and what should be done and how we should collaborate, uh, and then we struck a deal, and then over last 5 years I have done research work for them worth more than 1.5 crore rupees. So it just kept on increasing. It started with a small project, and they just kept on increasing the scope as they got different grants or funds from somewhere, and they kept on increasing scope of my work. But what I understood in Oxford, the way they work for on these different technologies, how they really work, uh, they have a big focus on some utility part of their research uh, and entrepreneurship part also, like what we call in India startups, they call spin-outs. The term they use is spin-outs, equivalent to startups that what we have. So Oxford University have many such spin-outs or startups which are initiated by students, by the faculty, and but all of them come under a ambit of a different company. It's not the university that is doing it. It's one company. That company name is Oxford University Innovations Limited. Some of you can even scroll on internet and find out the details about this company. So what this company does is a wonderful job. It's a company which is professional company, professionally run company, but 100% ownership is of the university. So university owns the company. So university has created this company. And now what does this company does? The people working in this company, they are not academic faculty. They do not go and teach anything. But what these people do, they file patents on your behalf. So anybody, any research going on in the university, the company people will come, understand what is the research. If there are any intellectual property to be generated out of that research, they will file patents or whatever copyright or whatever is required. They will try to sell that research to someone. They will try to get grants for that research. Now, the company being a professionally run company in that domain, they understand who can give research funding, who can give grants, uh, to whom we can sell patents or to whom we can license these kind of patents. And they collaborate with other experts to get whatever services they want. And that's how they landed on me. Otherwise, there is no reason for somebody in Oxford to imagine that there is a person in a small town in Dhule in India who is of their use for solar concentrator kind of technology. But that's the professional way of working of this company. And they float these spin-outs. They are a part of that company. Company had some share into it. And as I said, it's a professionally run company. So in a rupee term, last time when I saw maybe 2-3 years back, their turnover was more than 200 crore rupees. That was the turnover of this company, which is owned by Oxford Innovation, Oxford University, UK. Uh, while I have worked for last 5 years and still there is a project ongoing, I realize there is a similar need in India also. So in India also, we will need something like this, not exactly the same model, some Indianized version that can be practicable in India. But then that kind of development, research, entrepreneurship will bring a value in engineering colleges and engineering institute and universities, because then you create startups and uh, do funded research, do consultation, more of a consultation, and that will bring again a value, because our system, which is following what I can call placement, design for placements, will not work now. So that's another thought I just wanted to share, because we are talking about this. Uh, I like I recently I'm working in a domain of innovation to entrepreneurship. This journey of innovation to entrepreneurship, and I have been delivering sessions at different institutes. Like in last 2 months, I think I have delivered 8 different sessions, and from a small private institute, engineering college, to IIT Madras, all variety of institutes. I have realized that there are few terminologies people do not understand well. So I'm sure some of you must be knowing this, but again, some of the you who do not know, or the people who know already, but the significance of this in our engineering faculty, as a faculty or as a research scholar, what is the significance of this? So this one term everybody should anyway know. What is a TRL, technology readiness level? So when you have an idea in your mind, we call it as a TRL1, where you generate an idea. Okay. And then as you go up the ladder, TRL2, 3, 4, 5, what happens? Like your idea needs a validation, whether the idea is okay or technically okay or not okay. It is scientific. It follows the laws of science. Uh, so that is, and then it needs to be, you need to do some basic calculation and do some design. So this is all TRL2, when you verify feasibility, when you uh, basic design for some kind of a prototype. And then proof of concept, or uh, that is a lab prototype, normally we construct. Then there is another stage, it's slightly more than a lab scale prototype, where we say that okay, your idea is working in a lab environment, you see the idea is working. Then the next stage is a slightly bigger scale, we call minimum viable product. So minimum viable product is something that uh, see that the end application can be performed. And if you reach to that stage, next will be technology development, where you actually do working prototypes. Okay. And then working prototypes that you put into a field installation testing, as a normally TRL 6, 7. And then finally you do a product design, the engineering design, and do a commercialization, that is TRL 8, 9. So this is how we progress. Now what actually happens in our engineering institute, if I gave us some thought on this, and then I realized that uh, the undergraduate projects in many cases normally reach TRL 3 or 4. So you have some new idea, new mechanism, new for a computer people, maybe a new software or new app. You just do some basic things and make a small prototype kind of thing that works. You get some data from it, and that's normal. kind of undergraduate scale projects. So normally those kind of projects end at TRL 3, in some cases TRL 4. The people who are doing masters and PhD kind of work, the research that kind of goes in, they normally reach to a level TRL 5. In some cases, they can reach TRL 6. But that is my experience that, okay, they do a working prototype, extract some data from that working prototype, or we can call a test rig. And from that test rig, that data will be used, analyzed, and presented in the form of some thesis, and you get your whatever MTech or PhD, and normally it ends there. So in many cases, I'll say the research scholars will end at TRL 5, 6 levels. Uh, but in general, the amount of energy and effort we put into that research is actually not, it's not a good idea that the research dies down in your thesis at this level. So there should be some mechanism for our understanding of the people, that how to take this ahead to make it a commercially viable product or technology or business model, whatever it is. And this last leg is normally missing in our engineering education system. And as I said, now with a new trend, if we are to change our engineering system to more of an entrepreneurship based, this last leg is important for us to understand. Now, just try to understand, these are the different stakeholders during this journey. So you will need some people to do technical evaluation. You will need somebody as a designers, maybe manufacturing your prototypes, writing patent applications, writing grant applications, getting some grants. Now, getting a grant here at TRL 3, 4, 4, 5, I'll say, 4, 5, 6, is normally a research grant that you are going to look at. And in further stages, when you can go to incubation, mentoring, team formation, and final funding, that will be more like the entrepreneurship kind of grant. So it can be some kind of a equity or some innovation funding or entrepreneurship funding that will be coming in. People also do not understand the role of all these stakeholders. In most of the institutes, we normally have some system. They will have either center of excellence, they will have innovation labs, Atal tinkering labs, they will have some entrepreneurship development cell. So there are few things really happening. But even though these things are happening, they are not enough, or they are not in an organized manner. You need this to be in an organized manner so that no dots are missing, and then your ideas can finally be commercialized, or they get some commercial value out of it. Also, people do not understand the amount of funding that might be required during this journey. So this is my rule. You won't find it in the book, but this is my experience. That okay, if I call 1-10-100 rule, to reach to TRL 3, 4, if you really need 1 lakh rupee, normally these kind of funds will be bootstrap. So normally we will find student project at undergraduate level, they will pay from their pocket. But if you really go to TRL 5, 6, then you will need almost 10 lakh rupees. So normally people are not going to spend this, so they will look for some kind of a research funding or research grant. But if you really want from here to a commercial level, you will require 1 crore rupees. Again, almost 10 times. People do not understand the last leg, that they have spent substantially. You have a working prototype, working field working model, and then why we will need so much of a money? But believe me, you really need big money towards the last leg. Okay, so leaving that, there are different. These are the different avenues for engineering institutes from where you can get fund. Again, I'm sharing from my experience because I have got a lot of funds from different institutions for my innovations and commercialization of those innovations. So you have DST, you have different ministries having their own R&D departments. You have AICT, UGC, Vice Chancellor Innovation Fund. You have international research collaborations. You have CSR funds from the industry. But these two are of my interest, different innovation challenges and competitions. Those are floated nowadays. And there are private funding. You have seen programs like Shark Tank, where you have equity or funding, mostly from angel investors and uh, venture capitalists. And then there are many grants which are restricted to institutions or collaboration of institutions. I'll just show you some snapshots. This is a Solar X Startup Challenge, again, Innovation Awards for innovations in solar energy. Again, a big grant actually, 10 people getting $15,000 each, just as a award. So you are, it's up to you what to do with the award. But in most of the cases, it is expected that you should use that funding in developing your award or commercializing your product or technology. But again, this is recently concluded for, but this happens every year. This is restricted to solar energy. I'm just taking cases which are relevant to the today's topic. This Wilkes Climate Launch Prize, again, this is $500,000 award, again, for a climate change science. It is open, and I have seen many Indians winning these kind of prizes. But again, $500,000 around 4.2 crores nowadays. This BRET again is restricted to biotechnology, but they again talk about a clean energy, as you can read at the top. They give normally for last stages of innovations and enterprise. So I got 2-stage grants from there, like 10 contestants, shortlisted contestant got 5 lakh rupees each. So we got that grant. Then we converted our innovation to a field level unit. Another five contestants out of those 10 got 10 lakh rupees. So we got another 10 lakh rupee grants. And finally, 2 finalists are expected to get 50 lakh rupees each. This is for setting up an enterprise. Again, these are grants. So they give you money, and then it is up to you to use that money. But the first 2 stages are like you use 5 lakh rupees and then you compete for 10 lakh rupee grant. You use that 10 lakh rupee, develop it further, and then compete for 50 lakh rupees. Then there are institutions like International Solar Innovation Council. They give small grants. So this is more suitable for students because you are supposed to go only up to proof of concept or minimum viable product. So they give you up to 5 lakh, or they started giving in euro terms. But we got 1 grant for indoor solar cooker, around 4.5 lakh rupees we got from there. Then there are different competitions. This is one solar cooker design competitions were organized in 2019-20, and it's still follow-up going on. So from a Government of India instruction, they were done. So ONGC, Indian Oil Corporation, HPCL, and DST, they did different solar cooker design challenges or competitions. For DST challenge, we won that 5 lakh rupee award. But in other challenges, the different winners, those were like in Indian Oil, Sunbucket was one company which won, and then I was a consultant and to that company. So we also did some more design work for them. But these kind of things keep happening. We need to keep a watch to get some kind of funding from them for our research and for our commercialization of our research, converting it into some kind of enterprise. There are so many of these. I can give you at least 100 such openings from where you can seek funding. The strike rates are normally poor, like you may write 20, 25 proposals, then you might get one level of funding, but that level of patience anyway you need. Uh, and then you need a equity funding, now everybody knows about equity funding from angel investors and venture capitalists from this Shark Tank kind of show. Uh, Now I'll share my experiences in this kind of a journey. In most cases, like I think I have more than 24, 25 patents might be, and 10 out of them, 10, 12 actually, 10, 12 out of them might have been commercialized. Now, in most cases, this journey of commercializing any product or technology, in most cases, it started as a student project. So in a student's project, whenever we used to give projects to the students, they will do something, but they will normally reach TRL 3 because it was primarily the undergraduate students. So they will reach to some minimum viable product max or the lab prototype. By the time uh, their role is over, they will pass out, they will go, and it's our role. So in most cases, then I funded or I bootstrap, I put my money. In some cases, I got some grants, and then from there we used to develop it to a commercial level. So these are some domestic cookers. These are circular dishes. We call them SK14. That's a design of one Dr. Seifert from Germany. So we did not change his parabola, but we changed the frames and the structure. Then we converted these to something like these squarish dishes, which were easy to pack and ship. So on the lower right side, that I should have actually shown the box, but okay, it's a small box in which this could have been packed. But then finally we changed even that design to something like this, which you saw some videos earlier that I'm using at home. But this is primarily a commercial product. So a lot of my friends in other countries also using these cookers. Now this evolution, as I said, the early part normally done by the students. And I remember even that batch of students which did a prototype of this. They won IIT Bombay's Tech Fest competition, which is almost a Asian level competition. But that design and the performance of that unit won that. And then we extended, kept on developing to the final commercial product. So this is a more like a do-it-yourself kit with 9 joints, and we can ship it anywhere, and anybody can assemble it using the manual. Uh, my business model is slightly different because I'm not interested into typical manufacturing and selling systems. So I do my development work, and then I license my patents or technologies to interested entrepreneurs. So those are the people who actually manufacture and sell. But again, people should stick to their own strength. And a lot of time I spent in academics, so it was good for me to remain into research development and consultation rather than into manufacturing and that stuff. Anyway, that I don't like. So this is where the big money comes, as what I said earlier. In a commercialization, unit like this in the center can be fabricated, but unit like this, the fabrication will not require much of an investment. But unit like this, you need an investment like 30 lakh rupees we just spent in a die, which makes the profile of the dish. So 1/4, one segment of a dish. And here actually the big money comes when you need to commercialize your technologies. And we had lot of credentials with this, like these were used as a micro enterprise, where in indoor for making tea stalls. There are few tea stalls where people use these kind of cookers. Lot of people use at home. Um, and then sometimes you also feel like doing some what I'll call maybe a cracky things. Like I just wanted to demonstrate how good these solar cookers are. So, like in 2019, I took few cookers to Ladakh, to Khardungla Pass. Uh, that was a kind of a world record. We did solar cooking at the altitude of 18,300 feet in a Khardungla Pass. Uh, Very cold atmosphere, snow around because we were in an area, but maybe in some picture on the background you might see. But 18,300 feet elevation, you can understand the snow and the chilly weather and all. But we demonstrated that we can make coffee, and lot of visitors had that coffee. Another bigger version of this development is this Prince 40 solar cookers. Um, this I just showed you this one, that National Grand Challenge for Design of Solar Cookers by DST, that is Government of India, with a award money of 5 lakh rupees. Again, this was like the old versions were fabricated like this, with lot of strips and the reflector tied on the strips. Now we have a new version which is only 9 sections, 9 panels. They are connected to each other. So now this becomes easy to manufacture in a factory, easy to ship, and easy to assemble. And then we can do it anywhere in the world. So lot of installations in old age homes and tribal schools. But another, the biggest achievement I thought about the solar cookers was proving its worth in a solar trek in Nepal by a Dutch team. So they took the team from Netherlands took some of these cookers with them because they wanted to do all the trek on solar energy. So electrical requirement wasn't much. They just carried few small solar panels to charge camera batteries and all. Otherwise, primary need was a food. So the major area was the solar cookers, and this was very highly appreciated project, which I think 14 days they were moving with these solar cookers and cooking only on solar cookers all the meals. And very happy memories we have on this about these solar cookers from them. Then we did some projects with the help of Rotary in Uganda. I'm showing these pictures just to show some of the research and development features. Like these were made more like a do-it-yourself kit. So we haven't seen anything about these projects. We only on the internet and on the photos that the people sent us. We just send the material, they assembled on their own and used on their own. So they had in that one made college, they used 7 of these solar cookers to cook for 350 students. And now they will be scaling up to another 42 solar cookers to cook for 2,000 people. Another interesting project with this technology was like in Puerto Rico, where the island was hit by hurricane, something like this. The electrical system was down, the gas system was down. They normally have piped gas, and piped gas system was also down. And we were talking about using these kind of solar cookers in a crisis situation. And it happened, and then those people thought this is the right time to test. So they airlifted 5 of these solar cookers and then installed in their relief camps. And again, we had a very good pictures and feedbacks about the use of these solar cookers in crisis situation. So we did many projects with this technology. My TED talk on solar energy, 50% of the TED talk is on this. cookers and another 50% on another business model. That's not a part of the presentation today. But then we have similar to Wikipedia, we have wiki pages where these technologies are demonstrated. And this is something that many of our professors can also do. Like we had a concentrator or solar cooker we call, but basically it was a concentrator heat source. What can be done with the heat source? And few years back, we collaborated with a medical college here and then gave them this source for autoclaving. So they require autoclaving for sterilization of their tools and even biomedical waste. And they did 6 months trials on autoclaving on these cookers. And it came out really very good. Like they got some awards, they gave us certificates, they won some awards for this kind of research, some high quality research paper in elsewhere publication of Journal of Hospital Infection and all that kind of stuff. But then this kind of research can also lead to good commercial activity, because we had this much of a documentation. We did a few projects for installation of these solar concentrators in public health centers, primary health centers. So I think in Aurangabad and Jalna district, I think there were 23 centers. And then in some district, I don't remember exactly, might be Nandurbar, where we had 11 centers. But then this kind of research helps in convincing people that, okay, people can try these new technologies. On a bigger scale, we scaled these kind of designs and did 25 square meter dishes. These were for industrial process heating and community cooking. Now you will realize my earlier discussion about funding. The smaller units were done. Even this Prince 40, these kind of cookers, when we commercialize it, we got a private investor into our project. There is one Electromag group in Mumbai, and they invested 60 lakh rupees in this development. Here also, like for a commercially viable industrial concentrator, we required substantial amount. And again, we got a private investor into this. So ATE group of industries invested 150 lakh rupees at our end. They had few faculty, few staff at their end. So must have paid them another 1.5 crores or so. So total investment in the development might be 3 crore or of that order. And then we license patents to that ATE group. And this is how the finished commercial product looks like. And this is what they did, different projects in Coimbatore University and some other thing. This is not exactly my research, but my consultation. So this is the India's largest solar air conditioner, which is in Gujarat. It is a solar thermal air conditioner based on vapor absorption machines. So I was a designer for this, designer and consultant for these kind of projects. But these are the kind of activities I think all the faculty members should try to nurture, because they are challenging and they test your technical skills, and you enjoy the creative outcome when you see your product being commercially used, when you see your design being working in the field. You also enjoy that creativity. So there are some other which are not directly related to solar or partly related to solar. So biogas, I already shown you the one installation at my home. We use for kitchen waste, but it can be used for cow dung or for complete feed. Because it is at home, we are using on kitchen waste, but the installations in rural areas or in hotels, they are using on a much larger scale. This is again very innovative design, simple but very innovative design that won us some awards from Government of India, or some innovation awards. Uh, Again, scaled it up. Again, this is basically a design and not a development work. But then we did some projects where toilets were connected to the biogas plant. So instead of a septic tank, we asked them to construct biogas plant. So toilets and food waste was the input. And this ashram shala for 400 students saved 40% of their fuel because of such biogas plants. And then we did some consultation for village level biogas grid. So big plant at one location and then piped gas to every house with a metered connection. Then some projects into biomass gasification. These are the stores where we developed so around 7 different models of different sizes and different requirements. But you can see you use a biomass in a properly designed store, you get a very clean fuel. And primary fuel is also renewable, which is mostly the briquettes or pellets. Or you can have another design. These are gasifiers. Again, some of our friends with whom we work and do this development work. Now, one of my friends is Rahul Kulkarni. He has his workshop. He developed this gasification. Based on this gasification system, he developed this roti making, roti roasting machine actually. So they do this roti, they bake on this for, again, a big establishment like hostels or gurudwaras, or for the, again, pretty clean systems. So you get a fuel efficiency and you also get lower level of pollutions. And this is a one really interesting innovation I love a lot. This is a simple one, but I love that I developed this. So you can collect lot of waste in a standing posture without touching this. Again, I was saying, many projects started. This was one of the students' project, the Scheffler concentrator we had, and one of my friend, Professor Dubey, initiated this project. Involved some students to make a solar bakery out of those solar concentrators. So a lot of such things can be done. We are in a halfway process of developing solar commercial bakery. This is some other research work which I did, just to give you a message. A lot of us do our PhDs or different research. Your research should normally be focused on something that should be useful to someone. That's my attitude and approach. So when I was doing my PhD, I was developing different industrial systems using solar energy. And this was one multi-effect distillation that we were doing. And then this was an industrial oven. So developing one concentrator and few industrial systems, that was actually the part of my doctoral work. So it was the other way. I was already doing some research development work, and we just converted that into a PhD. So the only research papers, primarily, I think mostly I wrote only for while doing this doctoral work, and around 5 patents also during that. Patents anyway I was doing, but research papers I wrote only in that area. Because most of my development work leads to some commercialization. I don't really find much of a value in research papers as such. But that's another way of looking at your research, that your time, energy, money that you spend should not die in your thesis. So it should come out with something really fruitful, and it should pay you back in monetary terms as well as in some recognition. So these are some solar dryers that we developed. The one that I show at my home, or the here in the top, and that I developed collaborating with Sitara IIT Bombay. Actually, they had some funds, so they wanted me to develop a dryer for them. Now, these are all what I showed you, all were commercialized technologies. I'll take another maybe 5-10 minutes. I don't know how much time, but maybe I like to leave 10-15 minutes for a discussion. So these are some technologies now I'm sharing with you. They are at an advanced stage of development, but not commercialized. And why we do not commercialize it? Because in the last leg, as I said, you need huge amount of money. So either I should invest it on my own, and then after it is commercialized, I should do commercial activity and recover my money, get my profits, or somebody should invest it, and those people will get patent rights or technology transfer, whatever is required. So I'm sharing some of these ongoing innovations which are at an advanced stage. So this is one solar concentrator that we have developed, but it is still at a TRL. It's a 20. We did it first 10 square meter, then with 20 square meter, and that one grant I talked to you about the BIRAC, they gave us initially 5 lakh, then another 10 lakh, which we used here. And then this year we got the patent also. Now this innovation, like innovations can be different. There are line concentrators in the market, but this innovation creates a steam in a natural circulation, even though the receiver rotates. And that's a design innovation, you can say. And then as compared to the other concentrators of similar nature, where the aperture area is 70% or 80%, this innovation provides 95% aperture because it is placed inclined, so it can catch more sun. And then they are easy to manufacture and maintain. There are a lot of accessories which we have eliminated because we generate steam directly in the receiver. So we don't need a separation tank, we don't need a flash tank, we don't need a recirculating pump, and that's where the cost of the system comes down and system becomes more safer also. The another innovation that I'm doing with Oxford University, so I'm leading the team, and basically I'm doing a sponsored research kind of stuff. So they have a very unique design where two reflectors form a high temperature focal point in space, and which is fixed. The reflectors will turn, but the focal point will not change irrespective of any season. And that's the beauty of this design. So it actually all started, the Oxford University primarily had the physics, like the ray diagram you can call, that these two concentrators can form a focal point and which can be high temperature. Most of the solar thermal systems are for low temperature. Some concentrators that I discussed earlier, they are mid temperature, like up to 300. And this concentrator is for actually high temperature. We are looking for a high temperature space. So about 250, but we tested it for 500 plus for some application, like developing bone char for one university in Kenya. They are also working with Oxford, so they wanted to develop a bone char for arsenic removal from water. and we gave them this concentrator, and they could do it very well. High quality bone char they can produce. So I think I'll skip. This was a smaller unit. This was another big unit we manufactured. Like you can see, this is the aerial view we have, because from a ground we could not cover the one on the left. From the ground we could not cover in a camera the whole unit, so we just shot it with a drone. This 25 square meter aperture. This is how the structure looked like earlier without a reflector, and then this is with the reflectors. So at present, they authorize me to promote and collaborate with people in India if there are people interested in these kind of technologies. And this is my team. So I lead the team, but there are four uh, four professors. But this last name you will see, Mr. Chim Chu, is the guy on the right. He is a manager of Oxford University Innovation Limited. That's a company I talked about. So he is not an academic faculty, but he is an interface between us and the academic team in Oxford. So they understand from them, and they talk to us about the commercial part of it, the scope of the development, and that's how the system works. But again, I strongly feel we need to design some systems like this in our universities also. This is one idea I just wanted to share, but solar crematorium and incinerators. This is something which is on my mind for a very long time. And again, the reason is only Hindus do this kind of cremation where they burn bodies. So nobody else in the world has this kind of a requirement. So it's not that the Europeans or Americans are going to develop something, or Chinese are going to develop something, and we are just going to copy or import it. And this is something that we have to develop on our own, because this is our own requirement. But the project is very expensive, so it's still in a stage where I'm looking for somebody to invest. Recently, this NTPC, National Thermal Power Corporation, I think from there, mm, they floated some kind of interest in these kind of technologies. So let us see what happens. But we desperately need these kind of technologies, because we have like 80 lakh, or now the figure is still now more than 90 lakh now. They die every year, and they take around 30 lakh tons of firewood. The emission figures and everything you can understand. Uh, so this is something really looking at. Uh, to understand these systems, I actually visited a few solar furnaces. And these are solar furnaces in a remote area in France. This is a Mount Louis furnace, which develops 3000 degree temperature. And this is um, almost 50-year-old furnace. So again, still operative. So I just wanted to understand the design, see it, discuss with the people, the designers of this. And I was fortunately able to get right contacts. So I visited, have gone to them. So this is a samples they have kept in their museum, like melting of a railway track, or even the stone turning into lava. At the right side you can see. Uh, then we visited another furnace in that area. It's a Odelo, again in the same valley, where you can see there is a 7-story building, and one side of the building is converted into a concentrator, and this other building is there is a focus inside this another building which is in front. And then in the hill area, there are mirrors which divert energy onto these concentrators. And this furnace had a capability of 6000 degrees. The director of this unit, who just retired, he was hosting me, so I had a good opportunity to interact, see everything. This is a 20-25-year-old furnace, but mostly it is used in space research because they want atmosphere where there is no air but high temperature. So that's the kind of research they normally do on these kind of furnaces. There was one more furnace behind this which reached to 12,000 degrees, but that was used by their defense and space people. So that is nothing is available in a public domain, no photographs. But maybe as a special guest, we could at least see it from outside. So now the innovation status at my level is TRL3, where I have a design ready. And we are talking to these NTPC people and the other government agencies if they are interested into this kind of research, because the cost involved will be around 4 crore rupees. But then the research is primarily for a social cause, not a commercial one. So we'll see how it happens. We did some emission saving calculations and we found it is 3.5 times more than equivalent electrical fire furnaces used in crematorium. So those are the basic calculation that we did. Okay, I think I'm needing to the end, but because there was something about the climate change kind of topic, and I just wanted to give you some glimpses. This climate change or emission, people talk a lot about emission, people talk a lot about global warming and this kind of stuff, but all this, what time it is? Okay. So all this stuff, people in many cases do not understand this pollution, emission, global warming relationship with energy. Actually, it is the other way. Energy is something that is primarily responsible for all of this. The carbon dioxide works as a greenhouse gas, and because of the greenhouse effect, the heat from the earth cannot go to the space. Part of the heat is trapped, it comes back, and that is why the global warming is taking place. So we have to reduce our carbon dioxide emission. But then you see the relationship between the energy and the carbon dioxide emission. You do cooking, you burn LPG, which is a hydrocarbon, you emit carbon dioxide. You use automobiles, you burn petrol or diesel, you burn fuel, again you emit carbon dioxide. People talk about the EVs, electricity, but the electricity primarily still 79% electricity comes from thermal power plant. So electricity is primarily coming from coal. So when you use electricity, you actually emit carbon dioxide. Electricity in large hydro plants, people sometimes might feel that, okay, Sardar Sarovar is generating power from a water, no fuel burnt, but you have such a big reservoirs where there is a disintegration of biological materials, and you have methane emissions. And the methane is much severe, 21 times more severe greenhouse gas than CO2. Again, people talk about hydrogen as a clean fuel, but mostly you have to do hydrogen from water through electrolysis. So you use actually electricity, and then electricity is coming from coal. So there was a lot of criticism that people talk about hydrogen as a clean fuel or electrical vehicle as a clean vehicle, but the power is actually coming from burning coal. So how it is clean? And you might notice from last 3-4 years, people started talking about green hydrogen. Now, what is a green hydrogen? Mostly it is about getting that electricity from green source like solar or wind or something like this. So, but in general, you will find most everything that you do with fuels, everything that you do with energy, whether it is heating or electricity, you actually emit some amount of carbon dioxide, which is increasing your emissions and which is actually resulting into global warming. So this relationship everybody needs to understand, that you cannot really control global warming without doing something about your energy. So your energy has to be clean. So maybe solar, biogas, biomass. These can be the better sources as compared to uh, even the hydro. You need micro hydros, micro and mini hydros, not mega hydros. So you need those kind of sources for energy so that you don't burn fossil fuels, you don't emit carbon dioxide. Say fossil fuels, you have two sides. One is the emission side, but the other is also they are not infinite. You have a limited resources about your oil and coal and all that kind of stuff. So they are going to be exhausted at some point of time. So you have both sides to that energy understanding. But whenever you talk about energy, you should understand this relationship. Fortunately, the solar energy in India, in the world, has become the cheapest source at present. Like when we were consulting to the ministry in around 2010, when the solar mission was announced, uh, the cost of a solar panel was 240 rupees per watt. In 2014, there was a technical breakthrough in polishing wafers, silicon wafers, and the cost came down to something like 36 rupees, from 240 to 36. And then within 2 years, it came to around 24, 23, 24. Today in India, um, even after paying 40% import duty, you will get imported panels at 20 rupees a watt. And so that kind of drastically cost has reduced, and solar energy has become the cheapest source. That's a fortunate thing, we will say, for a mankind, but that is something you need to really understand. And again, well, we should understand what is the carbon emission from different sources. So these are the thumb rule figures. Like in India, 6-7 years back, not 6-7, 10 years back, the emission from electricity, because electricity come from different sources. Some are polluting sources like coal, a big hydro and all that kind of stuff. Even the gas turbines. In areas like Ladakh, you have even big 2 megawatt kind of diesel generators. So they are all emitting CO2, and there are some sources which are not emitting CO2. So uh, some 10 years back, uh, it was around zero point 0.9 kg of CO2 per kWh. Now, lot of solar installations are coming up because the solar has become so much cheaper. Now we have 0.72 kg now of CO2 per unit that you burn. So if you burn 1 unit of electricity, you actually release 0.72 kg of CO2 in the atmosphere. So electricity is also in no way a cleaner fuel. Okay, so I think this is all what I have to primarily say. Just sharing few things that I want, or I'm doing. I was doing during even my academic career, but I think you people also should do this in the faculty members. Like I used to write a lot in magazines rather than the research papers, because the magazines we are talking more about the practical things, something which is available, something which is commercially available. Research paper, we talk about something which is upcoming. So if further development is done, then it will come to uh, a commercial product or technology or something. But then I prefer to write a lot about magazines and newspapers. But that is, you should also do, because that also creates a good image in the society. Like I wrote a lot of articles for the newspapers also. So you talk about policies, you do all these kind of stuff, and then it helps you upgrade yourself, your knowledge, but again setting up you in the society, in your area of expertise. And then we used to do some of these activities when I was in the institute, do some solar canteen kind of program, take some solar cookers to the institute, cook on them, so people see, they get a confidence that okay, all these systems work. And a lot of things. I think we used to do almost like 3,000 idlis in a day. And then those students normally used to cook and sell those in the campus. But these kind of programs give you a practical feel. And some of people will really find that there are some enterprises, some enterprise coming out of those ideas. I do a lot of field training for the entrepreneurs in different technologies. Again, in a renewable energy segment. So these workshops are all hands-on workshop where people come, they do some construct something, do installations, and they do come from all over the world actually, not from all over the India. I get some participants from countries. After COVID, I'm really stuck up because I don't know, people are so used to everything online, whether people will physically attend these kind of training workshops. But again, these are something we can always do. And we do a lot of these kind of conferences, which are truly global in nature. Like I was one of the main organizers in 2017, and we had participation from 65 countries. So they were really global in nature. A lot of our conferences, we call them international, and hardly one or two speakers which are foreigners. But you can really do this kind of stuff if you have a right uh, circle that you have created. So I don't know how my audience has taken my presentation. Uh, it might be like I am patting my own back, blah 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 kind of stuff. But I seriously wanted to share my experience rather than talking something theoretical. So this is my strength, innovation, R&D, and then commercializing those things is my strength, and I wanted to share that. And because I did a lot of this work along with my academic career, so just giving confidence to some of you people that okay, some of us can at least do something similar. And financially also, I think I was benefited. At least in last 20 years of my career, I was earning much more through royalties and consultation and R&D than my salaries. So in always you set up yourself as a financially you benefit, but again you get recognition. You all those things will come along. And now what we are doing, and this is something, if it is useful to you, you may do this. At present I am doing trying to help people with this exercise of going idea to enterprise, because everybody has a brain, every people ideas keep coming. We do a lot of those things in projects and uh, different research, but we do not pursue it to a level that it should go to enterprise level. lot of good things are happening in institutes like IIT Bombay, IIT Madras. I have seen their entrepreneurship potential and the spirit is very, very good. More than 50% people are now going into some kind of enterprise. But this should happen at even lower levels. So we are trying to assist students and research scholars and even the faculty members how to do this. Many institutes already have good infrastructure. They have some innovation labs, they have tinkering labs, they have center of excellences, they have entrepreneurship development cells. But all dots are not connected. So whatever you have, you can utilize it. Whatever is missing, we can provide that support. So we conduct master classes for these ideas to enterprise. Wherever I can go, I can physically conduct those classes. Wherever I cannot go, I do online. We can provide you a lot of ideas. I discussed some of them, but I do have at least another 10, 15 feasible ideas for projects, for research scholars, primarily in the sustainability domain. So anybody wants to do some kind of a field research, I can give you some ideas. We can validate ideas and innovations in renewable energy and sustainability domain. So we have a team that can really do this. And we can provide a lot of information on the different grants that one can avail. See, there are some grants restricted to solar energy, some grants restricted to water, some grants in general about renewable energy, some grants more general like for a climate change. So we have information about many grants because we keep on applying. So we can share some of that information if your innovation and ideas fall into those domains. Thank you very much. These are my contact details. I normally respond to whatever comes to me. But if there are any questions, anything that we can do in a remaining time, let me know. Thank you.
Yes, sir. Thank you for informative session. Really, it's a good opportunity for our participants. Now the time to interact with our expert. So I request to participants, please interact with the expert. Whatever you are having the queries, please unmute yourself and interact with the expert.
Hello.
Yeah, go
Hello.
ahead. Yeah, I can hear you. Go ahead.
Yeah, evening, Dr. Chandak, sir. Sir, really, it was very impressive and very nice work done by you, sir. Hats off to you. We supposed to take inspiration from you to work like, a robot, yeah, come a person. Sir, really, you are an inspiration for all of us. No questions from my side. It was only the takeaway from you for me. Thank you, sir. Thank you very much.
No, the real thing will come when people will start implementing something.
Really, sir. It's true,
Yeah,
sir. Very.
see, I'll tell you about one experience apart from what you do. If you do some kind of a field research, you really enjoy. Like, I can't explain you, but somebody sends me a photo of my solar cooker being used in Portugal. The delight or that you get that, okay, it's your baby, your product, somebody is using it, appreciating it. That's another creativity that you enjoy. And I think everybody has a brain, everybody can deploy and enjoy that creativity.
If every technocrats works like you, sir, definitely India will become superpower within a few years of span. And it's true, sir. Thank you, sir. Thank you.
Really, sir, whatever today you are sharing, your experience and how to start the journey with the researcher to the entrepreneur and how to set up that entrepreneur and commercialize the product. That is a really good thing because most of the researchers, they are doing the work and they are doing or they are publishing the paper. and up to that, the limits only. But instead of that, how to commercialize the product and how to it will helpful for the society. It is a really good thing, sir. Participants, if you have any queries or interaction with the sir, please.
Are all participants from your institute or they are from different
No, sir,
institutes?
we are having the participant from the 6 to 7 states, Rajasthan, Gujarat, Madhya Pradesh, like that only. The total number of 188 participants we are having.
Okay. I just told you that these days I am conducting these sessions on idea to enterprise. If you find some value that for the students who are normally registering with those entrepreneurship sales, the students who are supposed to do the projects at third year or final year level, the research scholars, and the staff handling these activities, they are normally the audience. So if any other institutes feel those sessions, they can contact me. We can plan for those sessions whenever possible in physical mode. If not possible on an online mode, we can do that. Okay.
Yes, sir. Definitely, I will share your details to all the participants, so they will having the advantage with your expertise. Sir, I am having one question, sir.
Yeah, go ahead.
Yes, sir. Sir, whatever the research is going on, I think what is the status of material research in the field of solar energy, material development that is a reflector in India, and is any scope to develop the material like for reflector? And if we want, then how to start that thing from the basic?
See, about the research in solar domain, my take is we should do it in primarily in solar thermal area. That's one. Why not PV? Because the whole world is doing on PV. And as I said, I was a director on board for this International Solar Energy Society, and our meeting used to happen in the city of Freiburg. We have a institute, Fraunhofer. Now, this Fraunhofer Institute had 600 professors and only 500 research scholars. So not even one person doing PhD with one professor. They were so less. But the kind of research used to happen there was mind-boggling. Now, the amount of money, the amount of the other resources, like you need to test a solar module, you need an artificial sun, which has an intensity of 1000 watt per square meter, and your wavelength profiling matching close to sun. It won't exactly match, but now in those days, 2014 kind of stuff, one artificial sun used to cost something like 20 crore rupees. Now, how many people, how many institutes in India will do it? Our total infrastructure cost, I thought about the Fraunhofer, not exactly that, but bare minimum, still it was more than 200 crore rupees to set up some test facilities and this kind of research. Plus the kind of expertise. Now 600 professors working on only on solar energy, mostly funded. They were getting only 10% money from government of Germany. 90% their own, and the director used to say with pride, it is a government who want to associate, that is why they are keeping their stake. We don't want their money. Yes, but sir. Okay, because they want to get associated, okay, the German government is also with you. So with this kind of research, we cannot compete. They will always be at least 10-20 years ahead of you because you are running short of the expertise, the short of the facilities, the funds that is coming to you. So we should normally do a field kind of works. Primarily in solar thermal, it is easy. Designing concentrators, cookers, designing applications for them. That is more easier than going into a classical research of increasing cell efficiency, increasing reflectivity of materials. That is really taking a lot of money, and maybe still you will be left behind from the other institutes. So I look more into a simple common sense application side rather than a very typical academic research side.
Yes, sir. Yes, sir. Thank you, sir. Participants, if you have any query or we want to interact with the expert, please. Otherwise, we will go for the next session. Okay, sir. Thank you for accepting our invitation with a short communication
Nice to
and
interact with you
delivering
all.
the nice
Thank you.
informative session. Yes, sir.
Thank
Yes,
you.
thanks. Now, dear participants, we are having the one more session today. For the next session, we are having the expert with us, Dr. Biradar Madagonda. So I will introduce to today's expert. Then after that, the sir will start the session. So Dr. Biradar has completed his PhD from the National Institute of Technology, NITK, Surathkal. Then masters from the Dr. Babasaheb Ambedkar Technological University, Lonere, and bachelor from the Vishwesvaraya Technological University, that is VTU. Sir is having the expertise related to the solar or thermal field. Related to experience, sir is having the more than 11 years of experience to the different engineering colleges, professor, assistant professor, research scholar, likewise. The achievement, sir has already conducted the 2 FDPs. Then he has delivered the various lectures in various programs. He has conducted the workshop for the students at NIT Surathkal. Then STDP for the students at NIT Surathkal based on the heating, ventilation, and air conditioning and refrigeration. Then he attended the number of workshops in his career. Regarding the publication, sir has published the 12 plus paper in the SCI and Scopus journal, having the good impact factor like 8, 6, like that only. So I welcome to sir, and I request to sir, please share your knowledge that will be helpful for our participants. So sir, the time is now with you, and you are having the time up to 9 o'clock. So please, sir.
Thank you very much, sir. Thank you for giving the nice introduction, sir. I really thank you giving me the opportunity to become a session chair for this Atal FDP. Thank you all, sir. My screen is visible, sir. Yes, sir. Good evening, all participants. I welcome you all for this 6 days online Atal FDP on the topic of Industry 4.0 in energy sustainability and climate change. Moreover, the today's topic is regarding the subcritical, supercritical CO2-based solar thermal system. I'm going to just discuss regarding what the development happening in this field. So before moving to the my further presentation, so my presentation will be it will be like we are discussing about the introductions and what exactly the literature happened in with the different researchers overall throughout the world, and what was the gap which we found, and the objectives, and how we do the research or the methodology we conducted for our solar thermal system with the subcritical and supercritical. And also we are going to discuss regarding these results and discussions which we got, and we'll move for the question answering session. Just before that, okay. As we all are aware of this energy sustainability and climate change, because nowadays even the earlier session speakers, they have nicely taught regarding the development of the all the technological developments. Also, there is a like a growing the population, so which requires the more demand of the energy. So everyone today, even right now we are having the FDP online, so we are using the it may be mobile or the laptop computer systems. So where we are utilizing the energy, means we are burning the directly or indirectly the hydrocarbons which require for the energy development. So everyone require the this energy for the it may be like the luxurious life or the, even the basic things which we need for the day-to-day life. It is increasing very drastically. So even in the world we have the questions. The questions arises like what will be the next if instead of we are using these energy sources continuously for our developments or for the any luxurious life. So somewhere there is a scarcity of the energy which is available right now. So it is a very big question to all the researchers and the all the scientists. So that's why in world hardly not more than 2% people, they're working on the energy, means how we can save the energy or how we can increase the efficiency of the any systems or the any subsystems which we use for the day-to-day life, or it may be like a domestic as the or the industrial. So if we see this figure, the energy consumptions worldwide from 2000 to 2022. So you can see in terms of the consumption in exajoules, which is almost 1 exajoules is almost 2.7 into 10 raised to 11 kilowatt hour, which is very big. Okay. So in this, we can see the dramatic or even means the energy how we utilize. So this is nothing but like consumption and the drastic change in the energy utilization, which arose from even 401 to 635, or means it is the prediction up to the 2050. So right now we are near to the 2025, so which is almost we are utilizing the 617 exajoules. Okay, so this is a very big. Out of that, if you see the different strips where you can see the different resources we are using as energy, oil, so which is almost there is no such drastic change in the utilization of oil. Currently, we are in as a 2025, near to the 2025. We are the peak where we are overall the world. We are using the maximum oil because even we are very scared to the availability of the oil and even the coal, natural gas also, because these are the non-renewable energy sources. There is a chances of depletion of these energy sources. So if you see again the hydroelectricity, currently we are not this is like a dilemma whether we should consider this hydroelectricity as a renewable or non-renewable, because again the water which is available, but right now even if you see the India also in the rainy season we get the plenty of means abundant amount of water, but again if it January comes, so there is a scarcity of the water. So somewhere setting the hydroelectricity power which is very expensive, so and which requires a more effort also. So if you see the hydroelectricity utilization in the energy which is coming from the hydroelectricity, which is almost same, because we don't have the we are not set up in the new hydroelectricity power as we are set up in the new solar panels in terms of different gigawatts everywhere in the India, so that we can install the or we can increase the installation. But this is not happening in the hydroelectricity also. So we are coming to the renewable energy. So people right now they are getting the awareness of this renewable energy sources because as I told earlier, means all are very scared regarding the available whatever the resource of all these non-renewable energy sources. As we see, the petrol price, which from last 10 years, it rose from the 50 rupees to right now it is 104.5 rupees. So, like uh, because the availability which is getting depleted, so that is the one major thing. So one should have the more focus. So that's why if you see the renewable energy sources which is gradually increasing, and in future up to like 2050, so we'll have the more renewable energy to utilize throughout the world, so which is very important. So if you see the primary energy consumption worldwide up to 2023, with the data which I took from the internet. So out of that, the China, United States, India, Russia. So these four countries are the major consumer for this energy. So if you see the China, so all the developments maximum like we are getting the all the like utilizing or the systems. Okay, they are producing from the most of the things we are getting from the China. China is the competitor to the India also. So there they are utilizing the more energy. Means individually, if we come to the energy consumption, so somewhere the India is in a third stage. So if we utilize the same whatever right now we are utilizing, somewhere later in coming years, so we'll be the maybe a second top of the energy consumer worldwide. So even though means we are using these energies for the good purpose or to the development, but at the same time, how we are generating the energy for the utilization, that comes into the picture. So somewhere we should have the question or the about the energy generation in our mind, and then we should go for the further utilization. As like everyone, even last session uh, chair or the expert, he was discussing about the solar cooker or the how it is happening. So everywhere we are looking for the generation of the this type of energy what we utilize without like harming the ecological system, because as we are discussing we have seen the G20 summit, all these different nations, they are coming together and they are discussing about the different issues like ecological imbalance or how to protect the ecosystem in a healthy way. Even we are thinking or we are seeing that the glaciers which is melting. So even if the glaciers melting, if the if, only the 0.5 mm or 1 mm of the sea level it increases, it will again disturb the aqua system as well as the near around the sea level, those who are staying or the all the living livelihoods. So that's why one should have the these in mind. Here what happens, we are utilizing the energy. So in that energy, as the earlier speaker told again, already some of the things already covered in the last sessions. Like we are using the cooking, we are using the LPG or even the wood. So whatever we are using, there also we are like burning the hydrocarbons. It may be wood or the LPG. Again, we are using the automobiles. So automobiles, one another way we are using maybe petrol, diesel, or the currently the whole world. It is saying even India, it is more popular. That is zero pollution, zero emission of the e-vehicles. But for the production of this e-vehicle parts, everything, so there we require the consumption of the electricity, which is coming from the again the hydrocarbon. So even in automobiles, we are using these hydrocarbons utilization, so which will again lead to the increasing the pollution, that is increasing the CO2 in the nature. Electricity which we are getting, it may be from the thermal power plant or it may be from the hydro. So somewhere we are using this hydrocarbons and we are letting the CO2 to the atmosphere. So because of this, the pollution became one of the major issues in the worldwide. And for these things, we are only the responsible for that. Because see, until unless like we are disturbing the ecological system for our purpose, and we are increasing the pollution. So if we somebody, if you like travel by bike from even in currently we are staying in the Pune, like in a city from means maybe for 5 kilometers, somewhere we could see the pollution, how it directly affects to the human health. So that's why this pollution is a major issue, and out of to come out of this, one should think about the alternative things. And this CO2 again, maximum right now we are witnessing the greenhouses. So these greenhouses are most they are giving the part, or the these are the part of the increasing the CO2. So almost 60% of the greenhouse effect which is happening through the CO2. So we should come to the alternative energy sources. Like we have a different alternative sources. As I told earlier, the renewable energy sources and the non-renewable energy sources. These coal, petrol, diesel, these are the things which are about to deplete. So these are non-renewable energy sources. So we should move to the renewable energy sources like solar, wind, tidal, geothermal. So these are giving the availability of these renewable energy sources is abundant, and we can utilize it in a proper way. So if I come to the solar energy is very clean energy, so it won't harm the ecosystem. Ecological means balancing. Even we all know the D3 deficiency. If you are not getting the proper solar energy or light, okay, if you are not exposed to the solar, so somewhere we face the D3 vitamin efficiency. So means it is not only the growth of the plants, but for the human being, for the body cells which digest the different vitamins, we require the solar energy. So that's why solar energy is a source of clean and the sustainable energy, which is available abundantly. If you see the power which we are getting from the sun on the earth, which will be approximately 1.8 into 10 raised to 11 megawatt. It is very large. We can meet the demand of the whole world. But the thing is, we are not utilizing this solar energy in a good manner. Hardly we are using not even a 1%. So we are using less than that. So that's why our concern is to, as we know, this is a clean and sustainable energy. So somewhere we should utilize this solar energy in a different applications, alternative to the other non-renewable energy sources. So if you are coming to the solar energy, so here we have the different applications like low temperature solar thermal system and the high temperature solar thermal system. If you see this diagram, here you can see the different it is divided into four parts in a circle. So where we see the solar water heater, solar air heaters, solar cooker, solar cooling systems. So these are we can utilize for the these are the solar low temperature solar applications or the utilizations which we can use. Again, if you are coming to the electricity or the power generation, where we use the power towers or the even with the mirror, different types of parabolic trough type collectors, concentric type of collectors. So these are the things we are using for the electricity purpose and also for the lightning. So we all heard about the green energy building. So in which what we are doing exactly like the application for the heating and the daylighting. So this is the one of the part which we introduce in the green energy buildings. So there we can have the natural lights and the natural heating and the ventilation. So that is a very important. So that's why there we are using the sunlight directly instead of putting on all these bulbs and all. So that is the one of the applications of the solar energy for heating, even air conditioning purpose we are using, and the lighting purpose. And apart from that, we can have also the building integrated PV cells, so that we can generate the electricity even for the household applications, or even we can put it for the grid if you have the good rooftop, so that you can connect to the grids. So these are the different applications we can have with the solar energy, so which are really good. And mostly the thing is the initial installment or the investment will be more, but the payback period is very less. Any system which is having the less payback period, definitely it will save the energy, and it will save the cost or the money which is going out of pocket, which we can save in the future. So this solar energy, which is I'm moreover I am talking about the solar water heating system. So in the solar water heating system, as we know, collector is the one of the part. Okay, so this collector part, it is not a new to whole world. It has started in 1767 by the researcher from the Sweden, who is the Horace Soso. So they developed this collector for the different purposes, and means to get heated the different types of fluids and all. So later, what happens in the 18th century? So there was we got the solar heater commercially, and after that, 1970, because of this crisis in the fuels, and spiking the oil prices. So again, the solar came into the picture. As we aware, e-vehicles. So it started in 18th century itself, but somewhere because of the dominance of this IC engine, IC engine. So somewhere it got suppressed. Then now after maybe before Corona or near around 2018-19, so again the e-vehicles demand means it is getting high. So it is a solar system. We know from the early days. Only the thing is the utilization of these things. Maybe people think about that like a solar water heater. The research which is happening, it got saturated. Even the earlier speaker, Dr. Ajay Kumar sir, told like in somewhere the research got saturated, but you can do the improvement in the same area, so that we can increase the efficiency of the existing system, or you can have the you can utilize the different materials to increase the effectiveness and the performance of the system. As we know, means even we know the solar flat plate collector and the evacuated tube collector. So there are these are the ETC, which is evacuated tube collector. This is the next part of the flat plate collector. We say that the flat plate collector is having the less efficiency than the evacuated tube collector. But where we require the maximum installation for the solar water heating purpose, where the installation capacity is more. So there the flat plate collector is most suitable because it is a very cheaper compared to the evacuated tube. And also this evacuated tube which would sustain for the high pressure. So that is one of the major part. So where the flat plate collector plays a very important role. If you see, this is what the scenario of the flat plate collectors and the evacuated tube collectors. So one should move forward to how to use the flat plate collectors in advanced mode, or we can improve the efficiency, and because everyone we require the cheapest one. Whatever the product we are purchasing, it should be having the less cost, and at the same time it should give the a better efficiency. So that's why with this we got a motivation. So later we'll part about those things. So before that, I want to discuss regarding the heat transfer. So we all know about the solar systems. So even it may be a cooker, or it may be like a solar panel or solar water heating system. So there the heat transfer takes place, because even in a solar panel, the radiation falling on the panel and it converts that heat energy into electricity. In cooker, again heat energy transferring to the material or the medium which is available inside the cooker. Okay, so there is a transfer of heat is very important. So this transfer of heat we can classify into the forced circulation loop and the natural circulation loop. If you see these diagrams, so where the top right, so here it is having the solar water heating system, that is a flat plate collector, which is having the pump at the bottom. Okay, so normally what happens, the water which is coming from the over tank to the flat plate collector here, then it gets heated because the solar radiation which is falling on the collector, and it gets heat, and due to the buoyancy it will go inside the again storage tank. That hot water we can utilize for the different applications. Okay, so this is one where we are using the pump. So pump is again utilizing the extra energy. Somewhere like we are consuming the more energy than the what we use the normal solar water heater system. So again, it comes into picture regarding the maintenance of these pumps. Again, the cost of these pumps, then the storage, everything, and the bulkiness of the whole system. So this comes into the forced circulation system. So we are as a blower or the pump we are using in a different applications, maybe in a industry purpose or the household purposes. So it is a little bit costly, plus the like energy consumption will be more. So if you come to the natural circulation loop, where we are removing these pumps, if you see the bottom left figure, where there is no pump, means we are removing the pump so that there is no cost of that pump purchasing, and there is no cost of the maintenance, and even the electricity which we are consuming for that. So which will be most suitable for the different applications. Even if you see the nuclear reactors, like we have seen, I have visited to the BRC, Bombay. So they're using this natural circulation loop for the cooling purpose, which is very important. Means the natural circulation loop is having the more advantage than the forced circulation loop, and because there is no any moving components, pumps, compressor, which are not required for that. So before moving to the next part, as we are right now, we are seeing the solar water heating system everywhere, throughout the world on the top of the house or the floor. Okay, so where we use it may be like a solar flat plate collector, or it may be ETC. Okay, so there what we use, so these type of solar water heater, we are using water as a medium, so that we call it as a direct type of solar water heating system. So here, if you see any figure of any figure, it may be with a pump or without pump. What happens here? If you see the right top, okay, water is coming from the overhead and it will get heat in the collector. It gets heat and it goes to the storage tank again, and that water we are utilizing for our applications. Suppose right now we are witnessing the winter season. If you go to the places where the temperature is very less, sub-zero conditions, or where the temperature less than the 4 degrees Celsius, so there it is very difficult to manage such type of water heater. It is very difficult, because what happens in a night, whatever the water which is available inside the collector or the tubes, it will get freeze. Okay, there may be chances of again bursting the tubes, because whatever the collector we are using, we can't insulate at the top. So here on the top we can't insulate it. So that is one of the biggest problem, because we should get the solar energy from the sun, radiation from the sun. So there may be chances of freezing the this type of solar, means water, freezing the water in this type of water heater. So what happens in the morning time, we require the more driving force to circulate the water, means or to get the heat. So there the effectiveness of the system will get reduced. So this is the major issues. We can't use the water directly in the solar water heating system, because almost in a world 80% we are using the solar water heater system for the heating the water. So somewhere like even we are installing the heater to the water heater. Okay, so that is again we are using the, it will be like a forced circulation, or we are using the heaters. Okay, so I'm not talking about the forced circulation system. So in the natural circulation system, because of the freezing of this water, it is very difficult, and again which will cost more. So that's why we have, means we discussed, and we got to know, means even as I told, the natural circulation loop, which already they are using in the BRC to cooling purpose. So why can't we use this natural circulation loop with a different fluids? So if you use the different fluids, then you should not use the such type of, right now whatever we have the direct type of solar water heaters. So instead of these direct type of solar water heater system, we should go to the indirect type of water heating system. So if you see the right bottom figure, you can see the storage tank where we have the heat exchanger. Okay, so this natural circulation loop which we utilizing, so which is in a like a closed loop. So instead of using the water, we can use a different secondary fluids, so which will again more beneficial for the users, and we will be get rid of the freezing of the water, maybe in North India or somewhere, the place where the sub-zero temperature is there. Okay, so mostly whatever the direct type of solar water heater we are using, they are most suitable in the summer, as well as like the temperature where it is more than 20-25 degrees Celsius. Even if you see in a rainy season, it is very difficult to get the heated water in the morning. Leave out the winter. So rainy season also it is difficult, and even in winter also it is difficult. Even though if you get the like a beam radiation or the diffuse radiation. So again, I'm coming to the part of that ETC. We normally like ETC where we utilize. So there the beam radiation required. So instead of that, beam radiation sometime in the winter as well as the rainy season not available. So in that case, if we use the flat plate collector, so there we can use the beam radiation as well as the diffused radiation. Okay, so this is about the indirect type of solar water heater which we can utilize for the future. So there what happens, like as I told earlier, so this loop is having a different fluid. Here we are using the CO2 as a working fluid, and which is getting heated sensibly by absorbing the solar energy which is falling on the solar collector, and due to the buoyancy effect again it will go to the solar tank, and with the heat exchanger it will exchange the heat to the primary medium or the primary fluid which we are utilizing in the solar tank. Okay, so these NCLs, natural circulation loop, are plays a very important role right now, as we know the climate change or the energy sustainability. So somewhere we should think about the increasing the efficiency or decreasing the utilization. Researchers, they are fighting or they are working very hard to increase the at least 0.5 to 1% of the efficiency of their system. It may be solar water or it may be other systems where the efficiency comes into the picture. So here the NCLs we can divide into different categories, like how, whether it is a closed loop or the open loop, or the different types of shapes where we are utilizing, or the fluids which we work or utilize for the working purpose in the natural circulation loop. It may be a single phase, two phase, or the it may be supercritical. And again, whether it is a single channel, multi-channel, and whether it is body force which we are applying, whether it is a gravity or the centrifugal force. So you can utilize depend on your applications. So I have shown the different shapes of the NCLs, like while cooling of the reactors, there we require the rectangular type sometime. Otherwise, if it is a very small thing, there we can have the, like even the tube and tube type, that is a toroidal loop. So these are the different applications of the NCLs and or the different loops which we can utilize in the NCL. So advantage of this NCL is over the post the circulation loop FCL. They are very simple. We don't want any external source like a pump or blower, which will again require the electricity. So that's why the NCLs are the simple, and they are means we are getting in a low cost. There is no any pumps at all. Then the circulation we get, which is improved one, because the density and the buoyancy force matters in the NCL, natural circulation loop. So naturally we are circulating the fluid, the secondary fluid which we are on which we are working, and the flow structures will be very simple. And regarding the safety concern in a natural circulation loop, almost we are like working with atmospheric temperature. So like if we use the closed loop, somewhere we should think about the safety concern. But if it is an open loop, then we are working with the atmospheric temperature. So that's why NCLs are more safe. But we have the disadvantage of these NCLs. That is low driving head. That is nothing but like what happens if you want to heat any fluid, consider any tube, inclined tube, or height, vertical tube. So as you are heating the fluid at the bottom, so suddenly it won't rise or it won't flow. So there, because it is having the more head and the density matters lot, buoyancy effect. So the driving head will be very low in the NCL. Because of this driving head, we get the very less mass flux, means the amount of fluid which flows through that channel or the tube, which will be the very less. And sometimes what happens, the instability. Even though if you get the driving head, so there may be chances of mixing the fluid, hot and cold fluids. So instability. If you suppose have the inclined tube where the fluid heats at the bottom and it continuously heating and it goes to the top. But at the same time, top means the fluid which got heated, which will having the less density, which will be at the upper side, and the lower side it is having the cold fluid. So there may be chances of mixing. So because of this, we get the instability. Researcher, they are working on this instability so that we can minimize the instability and we can get the more efficiency. And next is the low pressure, low flow regime. Because wherever we move to the heat transfer rate or heat transfer, the pressure temperature comes into the picture. So at what temperature and sometimes the pressure comes into the picture. So if the pressure is low, so somewhere the temperature also there is having again we have the equations. I am not going in detail regarding the thermodynamics. So in a NCL we get the low pressure, and because of this low pressure, the flow of the resin or the fluid is low. So these disadvantages we can come over with the proper research. So that's why NCLR means we already have the advantages and the disadvantage can be come over. So this is again the beneficial to the utilization of the natural circulation loop in a different applications. So for these NCLs, that is a natural circulation loop. As I told earlier, the indirect type of solar water heater. So there, the utilization of the or the use of the working fluid is very much crucial. So how to select these working fluids? So there are different fundamental requirements. That is low viscous. Whatever the fluid which we use, it should be low viscous, because if you have the more viscous fluid, so there may be chances of like settle downing the fluid at the bottom. So we should think about the low viscosity and the low freezing point. The freezing point should be low, because if we use the high freezing point, so in a normal atmospheric temperature also somewhere the fluid will have the different physiothermal properties which will again affect the efficiency of the system. And we should have the high volumetric expansion coefficient, which plays a very important role to carry the heat from one medium to the another medium. It may be like in a convection. So whatever the fluid flows should have the more volumetric expansion coefficient, that is beta. And the environmental friendliness, as really everyone we know, even in air conditioning refrigerants. Okay, so the era like it started with the different fluids, R12, R22, ammonia, R143A, different fluids we are using. So means it like a few refrigerants, they got vanished because of the unfriendliness to the ecosystem, which will again toxic to the society or the system or the ecosystem. So that's why we should think about the environmental friendliness. Then it should have the high specific heat and the thermal conductivity. It should not corrosive. If you use the fluid inside the any loop, if it gets corrodes, then again it is very difficult. That's why we should think on this chemical composition and the stability. And main thing is the cost and the availability. So like gold is having the more means conductivity of gold is more, but we can't use this gold everywhere because the cost and the availability. So that is one of the thing Means this is the one of fundamental requirement to select the natural circulation working fluids. Uh, so out of this, here we are using the CO2 as a working fluid. Why we are using the CO2? CO2 is having the high latent heat of vaporization. Then the freezing point, which is almost minus 78 degrees Celsius. If you come to the triple point, it is having around 56.6 degrees, minus 56.6 degrees Celsius, and which is having the more volumetric expansion coefficient. And the beauty of this CO2, which we are using in the natural circulation loop, is a critical point, which is having the 31.1 degrees Celsius and the 73.7 bar. If you see 31.1 degrees Celsius, almost it is right now it is ambient temperature. So this year we could witness the temperature more than 50 degrees Celsius, the atmospheric temperature. Okay, so means even the atmospheric pressure near around 31 degrees Celsius, we can get the better result from this CO2. So any fluid which are working near to the critical point will give the better efficiency for that particular system. So CO2 is one of the like a key working fluid for this, and which is having the low viscosity comparative to the water or other fluid also. We will go through the chart which is in the next slide. And it is having the high specific heat, thermal conductivity also high. As a ozone depletion, we have the 0 and the GWP is 1. So if you see the right side, we have the we all know about the triple point. I'm not going to discuss in detail regarding the triple point and the critical point. Only the thing is, today's topic is the supercritical fluid, where this CO2 works in this range. The right means if you see the bottom figure, so where the supercritical fluid. Okay, so here it plays a very important role for the different applications. So here we can use the CO2 at a different pressures also and with a different temperature. If you see, this is the data which we got from the NIST standard. Even we can get it from the REFROT. At the bottom, we have the carbon dioxide, which is a density almost it is near same to all fluid, and the C also, which is almost it is, if you compare with the water is in the 4.2 specific heat. Here it is having a 2.59 conductivity, which is little bit lesser than the water, but the dynamic viscosity, which is like a very less comparing with all the fluids, and the thermal expansion coefficient beta, as I discussed earlier. If you see here, the carbon dioxide is having the more thermal expansion coefficient than the other fluids which are tabulated in this. And again, if you come to the freezing point, it is having the minus 56 degrees Celsius around. So here it will get free. Means we can utilize even below 0 degrees Celsius up to minus 56.6. We can use this fluid in a liquid stage. So that is the beauty of this fluid. So if we compare this fluid with the water, because in a solar water heater normally we use the water, and how the CO2 is better than the water. So for that we have took the data from the REFROP, and we compared with all the volumetric thermal expansion CP, K. So if you see the first one, which is at a 60 bar, and the 283 Kelvin for the CO2, and the water, which is atmospheric temperature with the same temperature. So the ratio of CO2 to water, where the thermal expansion coefficient plays very important role, which is very high than the water, which is almost 101, and the dynamic viscosity, which is almost 0.07 in the CO2 to the water. If you see the water to CO2, it is more. Means the CO2 is having the less dynamic viscosity. That is the one of the advantage of this CO2. If you come to at a different pressures, because we talk about the subcritical, supercritical liquids. So here earlier 160 bar, which was the subcritical liquid stage. If you come to the 90 bar with the 313 Kelvin, so there the CO2 it enters into the supercritical phase, where again the beta value is much high than the water. At the same time, the ratio of the this viscosity, which is high at water and CO2. So same thing for the same pressure with a different temperature. If we compare these things again, uh, the CO2 to water having the better thermal expansion coefficient, which is again lesser than the 313 K temperature, but anyhow it is good than the water. So that is the advantage of the this CO2. And coming to the these means we are using the CO2 in a natural circulation loop, that is solar water heater system. Out of this, we have different applications. One, as we are discussing about the solar water heater system, comes into the solar thermal system. Then the geothermal power plant, where we can extract the heat from the earth crust, and we can utilize that heat for the power generation. Then even in a thermal power plant where we use the boiler and furnace, there we require the natural circulation loop to circulate the water. So in a boiler, we are heating the water into the supercritical phase, and we are letting into the different applications, or even for the power generation. And cooling of the transformer, which requires the natural circulation loop. Already the temperature will be high. If we use the forced circulation, again the applicant means the pump or the blower which we are using to cooling the transformer. So those things will get again heat. So that's why we should have the natural circulation loop. Then the electronic cooling. Nowadays we have the different electronic items. So their heating will be the one of the issues. Even we have the big data storage. There, the heating of the system, which plays a very important. There we can use this natural type of cooling system, natural circulation loop, and also we can use this for the heating, ventilation, and air conditioning, as well as the nuclear reactors. These are the applications of the natural circulation loop. So now we are coming to the our solar water heater system with the CO2 as a working fluid. Many of the researchers they have done the experimental as well as the numerical studies on the uh, CO2 as a secondary fluid or the working fluid. So here you can see the heat transfer rate at average temperature of 283, where CO2 gives the better heat transfer rate. The bottom line in the first figure, you can see that that is the water at a 1 atmospheric pressure, and remaining the inclined lines are the at a different pressure, the CO2. Means the CO2 gives a better heat transfer rate. Uh, this 283, which is in a subcritical phase, and the second graph, which explains about the average temperature of 323 Kelvin. That is supercritical phase. So in a supercritical phase, comparing with the subcritical, if you see the both figure, the heat transfer rate at a 100 bar, which is almost 1000 bar, okay, which is more higher than the water-based system. So it gives the the advantage of the CO2. Means we can increase the efficiency of the CO2 based system more than 400 to 800 times, or in a percentage with the water. There are some researchers, they have done the research. So just I have listed out different papers we refer for the theoretical studies as well as the for the experimental studies. So in all these studies, they mentioned that the CO2 based systems are working better than the water based system. even they they mentioned regarding the like nanotubes with the nanofluids, which will give the better efficiency than the water-based system. Even the magnetic array formed by the magnetic nanofluids are more efficient than the water-based system. So that is the major thing. But we can't use these nanofluids in a solar water heating system. Again, the viscosity comes into the picture. Then the conductivity also matters. Even like a viscosity which increases and the conductivity somewhere it decreases. So that's why we found the gap where all the researchers they use the direct type of water heater or water based solar thermal systems. So there are very scant of the research on the CO2 based solar thermal system, and mainly for the flat plate collector people are I'm not saying it is a criticizing, but flat plate collectors we can improve the efficiency with the different techniques. So that came into our mind, and we moved ahead with this topic. Even the exergy and the energy analysis, which was not up to the mark in the research. So that's why uh, this got with this we got motivated, and we started working on this CO2 based solar thermal system, where the we can increase the effectiveness of the solar collector. As I told earlier, like at a sub-zero temperature, the freezing is a major issues that can be overcome, as well as the early morning, whatever the water we are getting, heated water, which is having the low temperature. So that can be eliminate with the help of the our current technique. So this gave us the motivation to work continuously. So we had the different objectives for the flat plate collector. So normally what happens while installing the flat plate collector or any solar water heater system, we install in the south direction. Okay, and the angle will vary. Like normally people put for the 45 degrees Celsius, 45 degree, but there the latitude and the altitude comes into the picture. Latitude of the particular space which varies if you come from the south to north in India. So where I worked, it was latitude was around 13 degrees Celsius. If you go to the north, the latitude goes on increasing. So somewhere, depend on the location, we should change the installation angle. So that's why we considered that latitude plus 20 degree inclination for our system, so that we can do the research on that. And these are the parameters which we took for the consideration. And for doing the experimental, like it is very difficult because in a solar heating system, if you use the CO2, as we know, CO2 is having a critical temperature of 31.1 degrees Celsius. At the 31 degrees Celsius, it is having the pressure of 73 bar, right? So if you again heat the CO2, pressure will shoot up. At the same time, the pressure, temperature will shoot up, and pressure will goes more than the 100 bar. So it is very difficult to manage with the transparent medium. So that's why we should have the different materials. We use the stainless steel 304 310, which will suitable for the higher temperature as well as the higher pressure. So this is our model. And before experiment, because as I told, the transparency is very difficult. Means you can't see the change the phase or the pressure, everything in the loop. So there we require the analysis, which is like a simulation. So for the simulation purpose, we took this model NCL model, where the if you see the red one here inclined, that is the solar collector on which the solar radiation which is falling, and the heat exchanger, where the CO2 is exchanging heat to the water or the other medium which we are using. Mainly here we are using the water as a primary fluid. So there the secondary fluid CO2 will give the heat to the primary fluid. And we took different dimensions for that. So we made some assumptions like whatever the fluid circulating inside the NCL should be single phase, and there should not be any fouling. If fouling happens, then again that is the restriction to the flow of the fluid. Okay, so we did the energy analysis and the exergy analysis. Energy analysis is very important, as we know for the solar water heating system, like we can insulate at the bottom and the side also, but not on the top. So somewhere like whatever the energy which we are getting or absorbing by the absorber plate from the sun, so somewhere losses takes place in the collector. So there are different types of losses. If you see here, these are the equations. I'm not going in detail regarding these equations. So we have the top loss, bottom loss, and again it is depend on the transmittivity and the absorptivity of the collector or the collector material which we utilize. So that is a thing. So with this we can do the energy analysis and even with the friction factor. If you come to the exergy, like while looking for the cost or the efficiency of the system, so we should do the exergy analysis. How quality we are getting from that particular system. If you see the diagram here, the thermal conversion system, which is connected to the thermal source and the output reservoir, along with the ambient reservoir or the sink, where the energy and the exergy, which are connecting each other to balance the analysis for the exergy as well as the energy. So this exergy analysis, which is including the E in, E out, and the these are the losses. This E dot in is nothing but the energy which we are getting from the solar. Always means almost we are getting the energy from the solar plus the fluid energy, so which is a combination of the fluid plus the solar. Then energy out is nothing but the heated fluid which is going out of the collector, that is the E out. We have the different losses. These losses are like one is the we have the temperature difference between the sun and the absorber plate. Normally, because sun is having the more energy, for this exergy analysis, we consider sun is having the 6000 K temperature, and we are considering absorber plate as the sink. So there is a much difference in the temperature. So that is the more loss. Okay, that is the one of the loss. Then the destruction loss will also consider in this exergy analysis. That is, one is the sun to plate, another one is the flowing fluid and the absorber plate. Means that absorber plate which will absorb the energy, and there is a temperature difference between the fluid which is flowing inside the absorber plate. So that we are taking into the consideration. And also when the fluid flows inside the collector, so there will be the friction comes into the picture. This friction which makes the pressure drop. As we know, the heat transfer, which is again the depend on the pressure. If we get the pressure drop, then the efficiency of the system also get reduces. So these are the losses we are considering for the exergy analysis. And we have done the grid independent test because we should do the simulation. While doing the simulation, whatever we like ANSYS, we all are know about like number of nodes, how much nodes we have, so that the computational time we can decide. So if you have the more number of nodes, then the computational time will increase. So to have the optimum computational time and optimum grid size, so that the result, whatever we are getting, should be in a same manner. There should means a steady result should come. So we did the independent grid independent test. So out of we took here 1 mm as a grid uh, size. Now we are moving. So that was the first part. That is I'll discuss about the results of the 33-degree collector angle. So next is the we have the different collector angles. As I told, first is the we should know the latitude of that particular place, and depend on that we are placing the this solar collector, and we increase the that angle with the 10 degrees Celsius, 33, 43, and 53 degrees Celsius, and the heat flux. As we know, the solar radiation, which is coming from the sun up to the ozone layer, it will be almost 1360 watt per meter square. When it is crossing the ozone layer, so ozone layer to the surface of the earth, there will be the depletion of the this solar radiation. After depletion, we are getting up to 1100 watt per meter square. So taking this consideration, we took this heat flux on the collector from 400 to 1200, and with the different parameters as mentioned in the this tabular column, along with the emissivity parameters, wind velocity, so that it will help for the simulation purpose uh, and exergy analysis. We did the simulation, and we got the means validation. We have to validate these things with the earlier research. We validated with Dr. Vijayan results, who was the former scientist at BRC. So we were working closely together. They were working on the these reactors for cooling the reactors. So here we are coming to the results. Okay. Before going to the results, we should know about the pseudocritical region. Pseudocritical region is nothing but near to the critical point, somewhere like the fluid shows the abruptly change in its physical properties. So if you see the left diagram here, the blue line, which it indicates the sudden spike, okay, at 80 bar. So this is nothing but, as we know, the critical point of the CO2, which is 31 almost 31 degrees Celsius, and pressure is 73.7 bar. So near around this critical point, the fluid which shows the better efficiency. So that's why we could see the spike at 80 bar. If you draw the at exactly 73.7 bar, so which will be more spike than this 80 bar. So that's why we can see we can get the maximum specific heat from that particular fluid which we use for the applications. Also, we compared with the mass flow rates also at a different heat flux. We have taken 400, 600, 800, 1000, and 1200 heat flux, and we did the simulation. So there, if you see bottom at the this red line and the black, they are in the same line, because water, it is a water at a different temperature. 278 K is at a liquid, subcritical liquid, and 305 at a subcritical, supercritical. Supercritical, but it is only the, like we consider 270 at 78 as a winter condition, and 305 as a summer condition. But in case of the CO2, a 70 bar at a 278 K, which is a subcritical liquid, 70 bar at 305, which is a subcritical vapor, and 100 with the 305 Kelvin, which is a supercritical fluid. So we compared with the mass flow rate. So we could see the a better mass flow rate for the CO2 at a different pressure. So even we discussed this velocity counterflow for the water as well as the CO2. As I told the earlier, the like a winter condition, okay, where so the A is nothing but the collector outlet. Means we took the velocity counter at the collector outlet, and B is the center of the heat exchanger, which is only possible, means center of the heat exchanger, seeing the results, which is only possible through the simulation only. So that's why simulation is very important before going to the experimental. Even later, we can, once you get the simulation properly, then we go with the experimental. Even we could see there is a errors in the simulation and the experimental also. So if you see this velocity plot, so first one here, this A part, which is having the velocity counter of the water, where the velocity at the middle, which is very high, which is around the 0.07 meter per second for the water. At the same condition with a 278 Kelvin for the CO2 with a 70 bar, the velocity got increased because here what happens, that is the in a collector, the centerline velocity of the subcritical liquid CO2 at a 70 bar, which almost we see the 0.07 meter per second, which is much higher than the water. Water is having the 0.04 meter per second. So it occurs due to the lower viscosity of the liquid CO2 than the water, as we discussed earlier, because the thermophysical properties which really matters in case of the CO2. Again, same thing happens for the in a subcritical paper as well as the supercritical phase. If you see the right side, the contour plots, here in a subcritical paper, we have the more temperature at the center than the supercritical. So the the density as which matters a lot for the CO2. We could see the this Reynolds number also. Reynolds number is very important, which gives the relations of the inertia force to the viscous force. There, if you see the normally for the laminar flow, Reynolds number will be less than 4,000, and more than that it will be in a turbulent. So water which will work, which is having the less Reynolds number here for the subcritical liquid case. If you see the green line, that is for the water at a 1 bar, which is having the less Reynolds number. But in case of the CO2, it is having the more Reynolds number, which is in a turbulent mode. So for subcritical paper and the subcritical, supercritical CO2, we compare. So here we could see the higher Reynolds number at the subcritical paper, and again for the supercritical, we get the better Reynolds number. Means the where the viscous force, which is not dominating in the fluid, means inertia force is more, so viscous force is less. So that's why we are getting the better Reynolds number comparing with the water. If you see the ratios, where the RE for the CO2 at 70 bar to the water, which is around around 160 for the subcritical liquid. For vapor, it is 203, and for the supercritical, it is almost 262. If you see the temperature, because in a solar water heater, when you use the water as a fluid, so it is having the, because the conductivity, thermal conductivity is more for the water here, and even the Cp is more. So that's why we can see the whole like a red, which the temperature is around 291 Kelvin. But in case of the CO2, near to the wall it is red, and inside, if you go to the towards the center, which is less, because the conductivity which is less than the water. In case of the summer conditions, right side, we can see the temperature difference for the water as well as the CO2 at 70 bar and the 90 bar. And the bigger circle which is the center of the heat exchanger. So if you see here, center of the heat exchanger, we could see the like the heat is exchanging from which is the annular tubes. So where heat is exchanging from CO2 to the water, which is happens. So that is the one of the reason where we can get the better result from the CO2. And also we have compared with the Nusselt number. Nusselt number gives the heat transfer of the convection to the conduction. Means in heat transfer, moreover, like if it is a fluid, so we should focus on the convection. So here for CO2, we get the better Nusselt number, and for the almost for the water, it is 4.36, which is constant. Okay, and for the CO2, which is more in case of subcritical liquid, and for the vapor also, which is comparatively at a bigger side than the water. Supercritical, again, it gives the ratio. If you see, means it shows the convection to the conduction. Means with the CO2, we have the more convection. If the convection is more, again, the heat carrying capacity that heat transfer rate will be more, which gives the better efficiency of the system. Now we are coming to the energy. So in the energy part, so we have again the subcritical liquid, subcritical vapor, and the supercritical CO2. And we are comparing these results with the water. So almost the energy efficiency, as we know, the solar water, which is up to 60 to 70 or 75% maximum, not more than that. No. But here with the CO2, we could see the maximum energy efficiency. Here what happens, we as while discussing about the exergy analysis, we have seen that the temperature difference of the sun and the absorber plate, which is very high. So because of this difference, so there will be, means atmospheric temperature will be more, and the energy losses will be more. There the energy efficiency will is very less for the water purpose. In a CO2 case, the fluid temperature will be more, so that the difference will get reduced. So that's why the energy efficiency again more at a liquid case, vapor, and the supercritical case. If we see the exergy efficiency, which is so before going to the exergy efficiency, if we see the energy efficiency here, at a 50 bar, we get the more energy efficiency at a subcritical liquid. But in exergy efficiency, we get the less exergy efficiency at a 50 bar, and the blue line indicates the 70 bar line. Okay, here we get the more exergy. Both are the like opposite here, because in exergy analysis, what happens, the temperature, like a loss to the surrounding will be more as the pressure increases. So there the temperature also decreases. So because of this loss, the means the heat difference, means the temperature difference is less there. So due to that, we can see the more exergy efficiency at the subcritical liquid and also for the subcritical vapor plus the supercritical also. If you see the dimensional exergy, as earlier we discussed, these are the EX. Delta P is nothing but the pressure difference due to the friction, which is almost negligible. And this delta Ts, Ex d delta Ts, that is the temperature difference between the sun and the observer plate, so which is more. So that's why this destruction losses is almost 99 to 97%, so which is more. And remaining are very less. So this data for the subcritical vapor at a 70 bar. So this is the dimensionless exergy, which gives the idea of the how the losses happens. Okay. Even other losses we can correlate with the ambient temperature and the wind velocity. As the ambient temperature increases, as I told earlier, so their exergy efficiency get decreases, because as ambient temperature increases, the temperature difference between the plate and the ambient temperature, which will be very delta T will be very less. So that's why the exergy efficiency decreases. At the same time, the energy efficiency, which will increase from 76.2% to the almost 79.3%. So these are the opposite to each other, exergy and the energy efficiency. If you compare with the wind velocity, as the if we increase the wind velocity, normally we have considered for the exergy analysis at a 5 meter per second. Okay, so if we increase, means for the simulation purpose 0 to 8 meter per second, so both exergy and the energy efficiency get reduced. Exergy efficiency, which reduces from almost 78.1 to 77.1. So again, the temperature difference between the absorber plate and the ambient temperature. So with this, we can summarize that the CO2 based solar water heating system, which is having the better mass flow rate compared to the water based system. And in case of the supercritical phase at 100 bar pressure with the summer condition of 305, which perform better, and the Reynolds number which we got for the CO2 for the subcritical liquid, which is around 160 times more than the water, and for the subcritical vapor and supercritical, which is almost 204 and 263 respectively. And the Nusselt number for the subcritical liquid, it was around 14 times more than the water case in a liquid, subcritical liquid, and subcritical vapor, it is almost 20 times, and supercritical, which is more than the subcritical liquid and subcritical vapor, and also with comparing with the water. Even we have done the different simulations with a different angle. So just I will go. I am not going in detail because already it is the end of the session. Now it is 8:50. So here, even we did the simulation for the 33 degree, 43 degree, and 53 degree collector inclination, and we got the different results. So with the through these results, I can say the 43 degree, which is giving the better results in case of the Reynolds number or mass flow rate, even in the Nusselt number. So it shows that means instead of having the 33 degree and 53 degree, so 43 is having the better efficiency, which is the simulation data. So after that, experimental part, we have done the experimental, which was the very crucial part, because as I told, sir, if you allow me for 5 minutes more, so I'll wind up the experimental part also. Just
Yes, sir, no problem.
you know. So here, as we were discussing about the CO2. CO2 is having high pressure. So working with high pressure things, it is very risky again. So we have set up the this experimental setup. So initially it was like we did all the fabrication design with our own. It is not a regular solar water heater. We have designed accordingly the fluid which are utilizing for the purpose, and we have tested with the water based testing, where even if you see the the here we tested up to 150 bar, so which is very high pressure, means there should not be any leakage in that. Even if you get any leakages, again the pressure drop will be more, and you can't get the more good result. So you can see these are the like connecting the thermocouples and testing the setup with the various pressures. So this is we have we have made the in-house solar simulator along with the it will be like artificial solar system. So this is the setup where we connected the thermocouple, this one, the thermostatic bath, also the data acquisition system, along with the different variation of the solar radiation. So whatever I told in that simulation, 400 to 1200, so that we could get with this solar simulator. And this for the solar simulator, we use the bulb, which are almost same as that of the what we are getting from the solar radiation. That is IR radiation, everything should be there. So we selected the bulb, and we set up the system. And even with the pyranometer, we recorded the intensity. And because of this, some confident. So I have not put the experimental result here in the presentation. So here we see the Reynolds number as well as the Nusselt number. Reynolds number almost we got, means it is matching with the experimental and numerical and experimental. But as I told earlier, there is a much means little difference in the error for numerical as well as the experimental. So this is tube temperature we got, and also with the Nusselt number also we got the better Nusselt number for the experimental setup also. So with this, I'm going to conclude that the subcritical vapor with the summer temperature, that is 305, so 43-degree inclination, which is better than the other two inclination, that is 33-degree and 53-degree Celsius. And also the Nusselt number which we got, which is almost 5.8% and 2.85% more than the 33 and 53 to the 43 degrees Celsius. And for the Reynolds number, we got a better result for the 43-degree angle, but there is a error between the numerical and the experimental. That is 11% error we got, because maintaining with the high pressure, it is very difficult. Again, at the same time, we have to compare the water with all the cases of the CO2, so which is a very crucial part, and these are publication. Thank you. If you have any queries, I request all the participants. If you have any queries, you can ask me.
Thank you, sir, for your nice and informative presentation and delivered the lecture from starting the basic, and I think you covered all the thing, numerical, experimental aspect on the superscript and subscript of the CO2 based naturally circulated solar thermal system. So I request to participants, please interact with our today's expert, Dr. Biradar, sir. Dear participants, we are having the chance to talk or discuss with the Dr. Biradar sir related to the solar thermal power system. Okay, sir. So thank you for your nice presentation and delivering the nice session on the solar thermal power system. So participants, regarding the attendance, I received the number of message. Attendance is not updated and all these things.
Hello.
So yes, sir, please, sir.
Sir, very nice presentation, Biradar sir. But as usual, like you started with basics and covered all the aspects. Just I wanted to know in slide number 19, the delta T refers for what?
Slide number
19, 19.
So this delta T difference between the there will be the two fluids,
Hmm.
means the plate as well as the and the fluid. So temperature difference with the fluid inlet and outlet, that is the temperature, sir.
Okay.
Delta T is inlet and outlet temperature difference.
Okay. Thank you. And very exhaustive work you have carried out. On the
Thank
same
you very
side.
much, sir. I
Thank
think you have seen the work
Yeah.
doing the research.
Yeah, I'm able to witness that one when I was in NITK. Go ahead, sir. Good luck.
Thank you, sir.
Yeah.
Thank you very much, sir, giving me the opportunity to deliver the few things in front of all the participants. So, once again, thank you, Dr. Satish More, sir.
Yes, sir. Thank you, sir. Regarding that attendance, I tried to upload the attendance on the Atal portal, but I think from today afternoon that Atal portal is not working. That's why we are having the trouble to post the attendance on Atal portal. So might be tomorrow evening you will be all get the update regarding the attendance. Don't worry, if you not get, we will complete that thing before the end of the FDP, and you will be get the exam link and certification, all these things. So thank you, participants. Within short couple of the minute, I will share the feedback link for the day 3. So it is request to all the participants, please fill the feedback and give your valuable suggestion in that feedback form. So thank you once again. Then I will stop here our today's session. Good night.
One more thing, for the tomorrow sessions, we have the very informative sessions for the tomorrow, which is on the battery thermal management system. The expert will be Dr. Kabish Waidi, and also the development of the Sohines turbine for the hydrokinetic energy generation by Dr. Shishikukumar CM. So I kindly request all the participants, please join before the time, means before 5:50, so that we can again start the session at the right time. Thank you all. Good night. Mangati sir, you can turn off your video.